All right, so the last time we looked at efficiency, and I am more particular about your ability to calculate efficiency. That's more important to me. Remember that you can calculate efficiency in two directions for now at this beginning stage. One approach for calculating efficiency, and all of them are called radial approaches, radial. If you look at the DMU, say DMU3 here, okay, one approach for calculating the efficiency of DMU3 is to help DMU3 to reach the frontier. Now, obviously, if you go backward like this, it's going to be difficult for DMU3 to reach the frontier. So the only level where DMU3 can be on the frontier is between this section all the way up to that section. However, it's not every part of the frontier that is good for DMU3 to reach, because some parts of the frontier are not fully efficient parts. We'll talk more about it. For example, the gap, the vertical distance here, this vertical distance is not a good part of the frontier that is fully efficient. Why? Because this part here, any DMU that is here, DMU1 is using one staff and producing one sales. So if this person is here, okay, in between, say the middle, that person is still using one staff and producing 0.5 sales. So it means that DMU1 dominates whichever firm is here in between the origin and 1. So anytime you have a vertical section of the production possibility frontier, and at this side too, a pure horizontal section, it means that the firm is not fully efficient. For example, any firm here, which is after DMU6 on the right, okay, that firm is using 7.5, 7.6, 7.7, or 8 staff. Okay. And yet, it is producing 6 sales, just like DMU6 is doing. And yet, DMU6 is using a less number of staff. So that is why the vertical and the horizontal section are not really a good and perfectly efficient sections. These sections are called free disposal sections. And it's led to a whole new thesis and research because it creates something we call slacks. We'll talk more about slacks later. So it means that the sections that are important for DMU3 and 5 to be efficient is between this section of the frontier, DMU1, 2, 4, and 6. But even that, you got to be careful which one you give it to, because you got to give it to those that are in the same location as 3. That is why we use the radial movement. The radial movement is a movement from the origin. So the distance from the origin to the frontier here, and the distance from the origin to the unit there. So that makes the calculation a horizontal measurement. And when you go upward, it makes it a vertical measurement. This vertical measurement is an output orientation approach. And the horizontal measurement is an input orientation approach. Between them, there are other measurements which are not radial, but they are non-radial. So to measure the input efficiency of DMU3, I will go to the origin like this, the origin, and then move the distance to the frontier. And then I'll go to the origin again, and then move the distance to the firm. And last time we got to know that the distance to the frontier will give you something like 1.5, and the distance to the firm will give you something like 4. Now, when you look at that, we now go and look at how this is measured. So you can see that from here, DMU, let me use a different color. DMU3 if you look at DME3 here, DME3 basically is efficiency is a distance from the origin to the frontier. Now remember, even though it's the origin in this direction to the frontier, divided by the distance from the origin to the unit. Now I'm picking the origin from here. So even though I'm reading it at a 2, I'm picking it from the origin here, going this way. And this will give you a value of, say, in an input direction, will give you a value, let's say 1.5. So we are looking at 1.5 divided by 4. Okay. And this is what we mean by efficiency, input-oriented efficiency. You got to learn how to calculate this. Now, the same DMU3, I can also calculate its output-oriented efficiency. How? The distance from the origin to the frontier here, and then the distance from the origin to the unit there. But remember, even though you are measuring it like that, you read the values on the axis on the left here. So this is going to be something like, if you read the origin, it's going to be something like 4. Okay, is it 4 point something? Okay, so it's going to be, say, 4 point something, and then divided by the distance here, which is 2. Now, you would therefore realize that the output-oriented efficiency, if the firm is inefficient, the value becomes what? Greater than 1. Why? Because, and we said this before, because you are measuring the distance in that proportion. Okay. It's not shown here, but the value will be greater than 1, because obviously you can see that it's going to be a bigger value divided by a smaller value. A bigger value divided by a smaller value. And that is how you calculate. Now, please note that this calculation is only there when there is y and x axis. Take note. In a 2D plot, y and x axis. But you can also have an isoquant. You see, an isoquant, you don't have y and x axis, but you have something different. So this is a typical example of an isoquant. Now, then the normal isoquant that you know is a smooth curve. But again, this is not going to be a smooth curve. Okay. This will not be a smooth curve. So the normal isoquant is something like that. Oh, just something like this. That is a normal isoquant. But because DEA is a piecewise linear envelopment, just as we said, we will not take a smooth curve, we will take lines, like you can see, piece by piece, okay? Because of the principle of convexity assumption. So you can see that the axis will not be x and y, but it will be x1 here and x2 there. That is a situation where you have input focus. So in this case, your focus is on the input, and you would have normalized the output. When I say normalize the output, you would have considered all the units as producing the same output. So all of them are producing output, say normalized to 2, 2, 2, 2, or 10, 10, 10, 10, or 1, 1, 1, 1. So that your focus becomes on the input. So you can draw the input and focus on the input. In that case, the same definition of efficiency occurs. So the efficiency of a unit here will be the distance from the origin to the frontier there, divided by the distance from the origin to the unit. Don't forget that definition. Don't forget it. What if it is not input-oriented, but it's output-oriented? If it is output-oriented, that is different, okay? In this case, look at this. So the original output-oriented that I spoke about in an XY graph, that one is what you see here. So this is an X and then Y graph. And in that case, you are able to measure input-oriented and output-oriented on the same graph. Okay. But you can also have input-oriented graph alone, which I did before. And let's look at the output-oriented graph alone. Oh, it's not here. Okay. But the output-oriented graph alone will be something like this. You just have this. This time it will not be X and Y, or X1 and X2. It will be Y1 and then Y2. And in that case, you don't have an isoquant, but you have an output possibility set, which goes something like this, that, and then that. That is an output possibility set. And then when you're estimating the distance, again, it will be the distance from the origin to the frontier, then divided by, again, the distance from the origin to the unit, if the unit is here. So keep that definition in mind, because that definition will be it is the one that is producing papers. It's the one. It's so basic, but it's so telling. So any question on this before we go to today's topic? Any question? Let me just show you something I want you to do, and I want you to submit this. I want you to submit this. Select one organization in the public sector. Select one organization in the private sector. Okay. So I'm going to give you an example of one. Don't use any of these. An organization in the public sector, okay, could be okay, let's deal with the private sector. Okay. Private sector can be a bank. So when you pick the bank is the organization. And so the DMUs are going to be the banks. A public sector organization can even be, I was going to say universities. But the thing about universities is that you got some of them which are private, some of them which are public. But let's assume that we are dealing with public sector universities. And that's what you're supposed to pick. It can be IRS, revenues, can be police department, can be several other things. What you do now is identify a set of inputs that belong to each of the organizations. And please, list as many possible inputs and outputs as possible. No less than 5. No less than 5. Because in the efficiency analysis, you brainstorm. You understand? You brainstorm. And you come out with incredible, inputs. Of course, later we use correlation analysis and principal component analysis to be able to come out with which ones are the best. That's what you're supposed to do. Identify the inputs, identify the outputs of the DMs. And then identify what measures, we call it proxy measures. So if you identify that labor is one of the inputs, saying labor is not enough, what are you going to use to proxy measure the labor? Is it going to be the number of workers? If that is not available, is it going to be the salary of workers? Or is it going to be the hours the workers put in to work? So that's what we mean by proxy measures. Proxy measures is it going to be, if you take labor, for example, and I hope, Emily, you are trying to get a point here, because these things are normally efficiency analysis beginning. Labor is proxied by multiple things. Is it going to be the number of workers? Is it going to be the wages of the workers? But sometimes some people think that the wages are more poignant than the number, because the wages also carry the idea of the value. So you can have 10 workers, and these 10 workers, the manager generates more value to the company than the cleaner. Okay. So using their salaries will give you a better understanding, because their salary appears to have weight, importance attached to it, instead of just the numbers. Or maybe the hours. Okay. Is it going to be the hours of work? Okay. So for some companies, they will do a login when you come in and when you leave and all that. Days you don't come, days you don't. And you can use this to proxy. So you got to think about not just mentioning the inputs and the output, but being sure you are mentioning the proper proxy measures for that. And then comment on the shortcomings on any of the things that you detected. Okay. So, for example, you decide to use number of workers, but you realize that the number of workers is not a proper proxy measure, so you use wages. So you mentioned that. You mentioned that it would have been good to use labor, number of workers to represent labor. However, labor doesn't give a quality dimension, but wages gives a quality dimension to it. So wages is good, even though hours of labor can also be used. That sort of thing. You're an analyst, you comment. So that's what I wanted to do. If that is fine, we can now proceed with the real work for today. The real work for today. So this is the real work for today. It is not that I am so smart, but I stay with the questions much longer. This is Albert Einstein. And it's so true. I stay with the questions much, much longer. Much, much longer. So we're going to look at the real DEA. First thing we are going to do is we're going to start with the advantages of DEA. And then we'll look at applied example graphically. Look, if you check most of the papers, you realize that they do the same graphical analysis. And when you understand the graphical approach I'm showing you, you would have fully understand the thing, even in a higher level, either for a PhD, research, or even for research for publication, because that's the same thing we use at a higher level. Just that I'll break it down here. All right. So we are going to look at the advantages and disadvantages of DEA. And mind you, every disadvantage we mention, you will see that there have been ways to handle the disadvantages. So even though it's a disadvantage, because researches are underway to correct it, some of the disadvantages are no longer disadvantages, or they are in the process of no longer becoming a disadvantage. Let's look at the advantages and disadvantages. First, I'm sure you guys know that the word CRS stands for constant returns to scale. And the word VRS stands for variable returns to scale. We will dig deeper under them when we come to returns to scale. But the constant returns to scale was introduced by chance when they had their PhD students, Rhodes. Then when Rhodes was out of the scene, Banker joined the scene, and then they extend, the Banker is a very powerful, management scientist and a mathematician. They introduced the variable returns to scale. I think we've discussed this thing before, haven't we? Have we mentioned the difference before? I think we have. Isaac?
Yes, Doc, we have.
Okay, tell me the difference then.
For constant return to scale, we use an example whereby should a company be involved in a business, and then over a period, the returns are assumed to be the same in terms of profits.
Okay.
It's assumed to be maybe 200 over a period of time consistently. So in the first month, they had the same profit of 200, second month 200, the third month the same thing 200. That will assume a constant return to scale, but should there be a variation in the profits, that would be a variant return to scale.
All right, okay. So constant returns is when you do something to the input, the output will react in the same proportion. So a 20% increase in the input will lead to a 20% increase in the output, the same percentage reaction. The variable, the 20% increase in the input could lead to more than a double, more than 20%, or less than 20%. or equal to 20% increase in the output. So that is a variable. And this paper, the original paper was published, I've put it in the page though. The original paper was published in 1978 in European Journal of Operational Research, but this was published in Management Science, you know, and both of them are very, very top level papers, highly cited in the literature. How do you do linear program? How do you do DEA? Well, you are going to see that you use a linear program to run DEA. So bring all the knowledge, come on, the knowledge that you have on linear programming to bear. Bring it on, because those things are going to help you. One of the things about linear programming, if you can remember, is that there are constraints. Do you remember? There are constraints. Okay. There's a left-hand side, there's a right-hand side, there are slacks. There are slacks, there are, you know, input excesses, output shortfalls. They are there. And then you also have lines, because as the name sounds, linear comes from line. So there are lines and there are corner points. You guys remember, there are corner points, vertices, and the vertices are the key. And so every other thing is irrelevant, is the vertices. It is those vertices, those are where the DMUs are located in our case. Those are the corner points. And then you join each corner point to each corner point. That's what creates the frontier for the DEA. So if you know how to do linear programming, even in R, or in packages like Lingo and Lindo and MATLAB and SAS, if you know how to do linear programming quite well, which I can teach you easily with R, then it can easily help you to understand, not to code though, but to understand how it works in DEA. However, there are so many packages in DEA that does it easily, automatically for you. Where even if you don't have knowledge on linear programming, you can still do and understand and apply the DEA so perfectly for managerial policies, for regulatory policies, for research purposes, for theses, for publications, or anything. You can still do that. But I love to baptize you a little bit with some knowledge on linear programming. That way, you will be able to understand behind the scenes what is happening. So let's see how it works. First, let's look at advantages of DEA. By now, you will know that one of the advantage of DEA is that it's very easy to use. Because we just took some data last time and we're even able to calculate the efficiencies. But you see, the fact that it's easy to use is also a negativity somehow, because when something is easy to use, a person can misuse it because it's easy to use. For example, if it is easy to fly an aeroplane, then there would have been a lot of accidents. Because it's not easy to fly an aeroplane, that is why the number of aeroplane accidents are way less than the number of car accidents. True or false? So, because it's easy to learn to drive, that's why there are more car accidents than there are when it comes to something related to this. So, very easy to use. Okay, that's an advantage. The second advantage of DEA is that it can, and this is big. Do you guys remember when we're looking at the stochastic frontier analysis and the ratio analysis, we indicated that if they are used to dealing with one input or one output at a time, DEA can deal with multiple inputs and multiple outputs at the same time, which is good because in real market systems, in real life, companies and firms and organizations, they are using multiple inputs to generate multiple outputs. If you go to a university is able to employ or utilize workers. They have incoming students. They even have types of workers, types of incoming students. and they produce different outgoing students, undergrads, masters, PhDs, different publications, multiple inputs, multiple outputs. Number 3, you don't have to specify any restrictive, arbitrary parametric functional forms. I said it before that because stochastic frontier analysis deals more or employs a regression type approach, you got to deal with multiple from functional specifications. You got to specify the production function, if it is a production function. You got to specify a cost function. So sometimes you have to think about which kind of cost function you want to specify. Some will specify, translog function, transcendental logarithmic functions. Some will specify Fourier flexible functional forms. Like, there's so many. And then when you specify, you have to also specify a functional form for the error term as well as for the inefficiency term. Whether it's normally distributed, whether it's half normally distributed, truncated normally distributed, McFadden normally distributed. You've got to make a lot of assumptions and a lot of specifications. And that can be tedious, man. And then you impose some restrictions on the production, function as well. But when it comes to DEA, as the name sounds, is data driven. So you are only allowing the data to talk to you. You are looking at the data and the data is speaking a beautiful language for you. It doesn't mean that there are no assumptions in DEA. They are axiomatic assumptions. They are foundational assumptions. And however, those assumptions are not restrictive. They are assumptions that make sense. We are going to look at some of them. For example, the assumption of convexity, the assumption of monotonicity, the assumption of redisposability. Oh, come on. Retention scale. All of these assumptions are very practical. They are not too restrictive. That's one thing you need to know. So that's number 3. Number 4. And by the way, anytime you are using a methodology or you are extending a methodology, it makes sense to actually indicate the pros and cons of that methodology. DEA can decompose efficiency, and later you'll learn that there's another version called productivity, which looks at time. It can split the efficiency you got into multiple parts so that you will know which of these efficiency parts is the main contributor of the efficiency of the firm. So profit efficiency can be decomposed into cost and revenue efficiency. Cost or revenue can be decomposed into technical and allocative efficiency. Technical can be decomposed into pure technical and scale efficiency. And technical can also be decomposed into mix efficiency. And cost can be redecomposed into different scope efficiencies. So they are quite different kinds of parts of efficiency. Now, why is this necessary? It's necessary because you are able to know what is causing the problem. If a person goes to the hospital, the person says, "Doctor, I'm not well," and the doctor realizes that the whole "I'm not well" has to do with the person's eye. The general practitioner will immediately refer the person to a specialist, an eye specialist, to handle the matter. It gives the person a holistic, a pure solution, a beautiful solution to the problem because there's now a specialist. So you are able to know which part of the body is not well, and you can cure that part, without affecting the other part. And it's good to know which part. The same thing with any company. You can determine which department is really driving the performance of the company. Is it the labor department? Is it a supply chain in general? Is it a finance department? Is it accounting department? Is it an HR department? Is it a marketing? And sometimes you can even detect when there's a problem, which department is causing the problem. DEA is so practical that it can allow you to do all of these part analysis. There's another advantage. Number 5, DEA is unit invariant. It does not depend on the unit of measurement. The last time I told you, if you are using ratio analysis and you want to calculate return on asset and return on equity, return on asset will be looking more at the total profit or the net profit divided by total asset. The net profit has to be in dollars. The total asset has to be in dollars. None of them can change their unit of measurement. DEA is not like that. It doesn't matter the unit of measurement. You can be working with dollars. You can be working with number of staff. You can be working with kilograms of bags. You can be working with the square feet size of a room and mix that with a metric tons of barrels of thing. Like it is unit invariant. And those papers I've just listed here, when you read them, you see that it helps to explain the standardization. You don't need to, any standardization. You don't need to commonalize the unit before you can use it. And it will still work perfect. It's very, very useful for that. Another thing, it is also very useful to note that even if you don't know the value of some of the items, so suppose you use the number of workers and you don't know what is the value of the number of workers relative to capital. So you have labor and you have capital. Which one is really contributing more for a particular DMU? DEA will generate relative importance, prices, weights. If the need is, if you need it, you will get it. Okay? Even though you don't need them, it will help you, and it can use that as a way to value the inputs and the outputs. And it's a very, very powerful, a very unique way, okay, that DEA does something like that. In other words, you can use it to price or to value something. Number 7, DEA is useful for target setting. You can use it to set target, because the thing is that it tells you that you are inefficient, but it also tells you what you got to do to be efficient. That word, what you got to do to be efficient, is a target. And it also will go ahead to tell you who are your peers you should emulate. Who are your peers you should emulate? What are they doing uniquely that you got to learn from? It tells you. It makes DEA very managerially useful. Company managers, supply chain directors, finance directors, CEO, they would love to employ this, to be able to help set targets for respective inputs and outputs. But there are disadvantages, there are demerits. And one of the demerits is that, and this was a long time ago that Farrell has indicated that the frontier that we determine is determined by a small number of efficient guys, if you can remember. So most of the time, forget about our example didn't reflect that. But most of the time, the frontier is determined by a small number of efficient guys, while most of the others are inefficient inside the frontier, inside the production possibility set. And this has been defined as being a great waste of information. It's like you ask for something, I give you that something, and you just take a little of that something. It's a whole new kind of work on that you can check later. Another kind of disadvantage is that DEA is deterministic. It is non-parametric, don't forget. So you don't use a parameter. Like in regression, you estimate the coefficients, the parameters, the estimates. You estimate them, and then you get a value for them Then you try to determine the significance of each independent coefficient and how it affects the dependent variable. So if DEA is an estimate, then we should be able to know the extent to which that estimate affects the performance of a company. But it's deterministic. Why? Because apart from estimating the efficiency, it attributes everything, deviation from the frontier. You remember regression will tell you that part of it, the stochastic frontier will tell you that part of the deviation is due to inefficiency, whereas part of it is due to the error term. DEA says, no, all of it is due to inefficiency. All of it. So then what it's saying is that there is no noise. But you and I know that there are possible noises. Okay. A company can be inefficient, not because managers caused that, but because there was flood. And that led to destruction of the harvest. So you got to capture inefficiency. And DEA, because it's deterministic, it makes it very hard to introduce noise and to handle inferences effectively. Having said that, though, there have been studies that have now been proposed to handle some of the, one of them is order M and order alpha partial frontiers. These partial frontiers do not, take the extreme outliers. We'll talk about outliers very soon. So the outlier, remember DEA is taking the extreme guys and they're using them to form the frontier. So this guy says, no, let's take not the extreme guys, but a bit of the guys, not to the extreme, because the guy might be extreme because he's an outlier. So he tries to do that. Then there is also the stochastic DEA, okay, that tries to introduce noise in addition to the inefficiency. These are all ongoing research as you speak to try and handle some of the non-statisticalizations of DEA. Still on the statistical inferences, we know that economic interpretations are very useful. And because the DEA doesn't give us proper estimates, it makes it difficult to economically interpret. Managerially good, but economically interpret. Because you see, economists love to know the impact of something on something. And it's not easy to actually make statistical inferences short. Okay. I've already spoken about the fact that the method itself is sensitive to extreme value, outliers. It picks the outliers to create the frontier. And once it does that, it means that even if that outlier is a bad nut, you still consider that bad nut as a frontier DMU. And you're going to measure the efficiency of others relative to that guy. That guy who is crazy and is a bad nut. You are now going to use him as a benchmark to determine the performance of others. You see the way the whole thing becomes flawed. Having said that, bootstrapping, and again, the partial sum frontiers I spoke to you about, attempts to solve this. Now, bootstrapping is a computer simulation, intensive computer simulation exercise that tries to create pseudo samples of the data. So the samples you have, it multiplies and create multiple versions of the data. It is mimicking the true population, which is unknown, the true parameter. So what the DEA says is that, what the bootstrapping says is that the estimate, the theta estimate that you got, this is just an estimate, but there is a true theta that is there, which is the population theta, which you have not gotten. But we need to get that because this very one is not known. But this very one is known. That's why you've estimated it. But the actual one, which is supposed to be used, is unknown. This is unknown. So let's get it. But we can't get it because it's unknown. So bootstrapping tries to create multiple pseudo samples, thousands of them, that is being found using Monte Carlo simulation, is being found to approximate the true underlying technology, which then means that we can now use it to represent this data, which is flawed, more or less, or is infected with some issues of not including noise, some issues of probably incorporating outliers. So bootstrapping tries to solve that. However, bootstrapping is not a panacea. And I've said it before, that it doesn't mean that when you use bootstrapping, it makes it magic and everything becomes solved. Because it's also heavily reliant on your data. So yes, these are some of the ways to helping. But for now, it is the only current one, or one of the few things that can be used to handle some of these issues. Now, there's something we call the curse of dimensionality. And DEA can suffer from that, because when the curse of dimensionality is when the number of inputs and outputs are more than the DMUs. So the rule is that the number of inputs and outputs should be less. The last time when we're looking at inputs, it should be less. And if they are less than the DMUs, the dimensions on which these DMUs are seated are few. And so it makes the DMUs be held, very well. And that case of dimensionality is always a problem for DEA because sometimes you don't have all the data. And so you can have issues of sampling variations, you can have issues of sample biases and other things. So, as most of these things, bootstrapping can help handle the issues. So that is it. Any question on the merits and demerits of DEA? Any question? It's very important.
The DEA being deterministic.
Mm-hmm.
So now we know that the partial frontiers and stochastic DEA can handle those.
Mm-hmm.
So is there any plan of teaching that partial frontiers to help us know how we can solve that problem?
Yes, I have plans, but I myself am learning it. I need to be honest.
Oh, okay. Okay, it's a new thing.
It is a new and also old thing. You see, most of these extensions are individualized. So a researcher chooses to know which area he wants to delve into. There are different sections of DEA. Somebody says, I'm going to go into the area of non-radial DEAs. Another will look more at the statistical sections. Some are looking more at cross efficiency. Some are focusing on productivity. Others are focusing on value efficiency. Others are focusing on fuzzy DEA. Others are more focused on weight restriction. So the extensions are many. And even though I know it is there, it is something that I've not deeply looked at it to master.
Okay.
But then I've looked at the bootstrapping, which is another way of handling the issues.
Okay.
And I'm talking about looked at it only in terms of application, not extension of the models, but in terms of using and making sense of it. So who knows? It is something that you might research into it and come and help us. Because I like those that look more at the stochastic DEA.
Okay.
Not just a partial for that. So I like it, non-parametric stone. There's a guy called Kusmanen, very, very intelligent guys, with Sema and Wilson. These guys have pioneered a lot the area of stochastic DEA, the area of STONED, they call it. Stochastic non-parametric estimators. So it's like there is now a gradual convergence of DEA and SFA. All right.
Okay, though. Thank you.
Let's go to the estimation process. The production possibility set. Please note that it is also known as the technology set. What you see here is the representation of the technology set. Okay. I'm using this Greek letter to represent the technology set. What is the technology set? What is the technology set? All right. So the production possibility set is this side here, PSI side. And we are going to use it, of course, please remember you can use anything. You can use any letter to represent. You can use P to represent the production possibility. You can use T. And there are N DMUs. So the total number of DMUs are N. Each one is producing S non-negative outputs. So we are assuming that you can have outputs that are non-negative, but there can be zero outputs. Okay. In fact, there can be negative outputs, but for this purpose, we are not considering. And these non-negative outputs are given by Y being a member of real positive all terms. And these outputs are consuming inputs represented by X, which are also real numbers. On the basis of this, we can define the production possibility set, the technology set, or the input-output combination set. We can define it as this, where the psi is a set of the input and output being a member of positive numbers in such a way that X can produce a Y. This is a general way of defining the production possibility set. We are considering both input and output as desirable. Desirable. If you don't understand this, let me know, because this is very important. You should know how to write the production possibility set for input and output. You know how to write it. This is mathematical writing of it. What are the inputs? The inputs are many, and each input for each DMU is given by Xij. Each input for each DMU. Okay, so you can have a DMU with 4 inputs. So in this case, I will be 1 to 4. Okay. And then you can have the same DMU with 6 outputs. And so R will be 1 to 6. So each R can be an input. The J is a number of DMUs. The Y is the output. So the YRJ is the level of output R that is produced by DMU J, particular DMU. The DMU is a dominating DMU, or it is a dominated DMU. A dominating DMU is the one that is using less input in one of the inputs, at least, or producing more outputs in one of the outputs, at least. So if you look at DMUJ here, and we will show the mathematical writing, the DMUJ is in such a way that it is strictly better on one variable. Strictly, not weakly. Better in one variable, and it's not worse in the other one. So in the other one, it might be less, but it's not worse, because it's less, but even though it's less, it's weakly better. That is equal to. So let's write that mathematically, because the principle of dominance is important here. A DMUJ dominates a DMUH. How? Look at it. J dominates H because J, Xij, is less, using less input, or at least the same input as that of H. So J is using less input than H. That is why we say J dominates H. But in addition to this point, the output as well, J dominates H if is producing more output than H. And in addition to that, it's not like it is using less input than H, but J's input are less for at least one of the inputs. They are less for at least one of the inputs, but not that all of the inputs. You don't need all of the inputs, but at least one of them. The same thing with the output. On the basis of this, we enter into the world of efficiencies. Guys, so we are going to look at the mathematical definition of efficiency. I know, we said it before. Now, the first mathematical definition of efficiency will be considering efficiency for only one input and one output. So let's say that you have one input and the input is X, and you have one output and the output is Y. The Y divided by X is said to be efficient. Let me ask you guys, how do you increase this ratio? What are the possibilities? Alex, how do you increase this ratio? One way to increase the ratio is to do what?
Doug, is to improve the either your output or your input. So either way it can work.
How do you improve? Be clear.
So if you can, for example, increase the level of output while maintaining the level of input, the ratio can improve. Or on the other way around, if you can also maintain the level of output while reducing the input that you are using, it can also improve the ratio.
All right. So that is one way you improve this particular ratio. You see, the reason why this is important is, and watch the word, improve or increase the ratio. Remember, we are not increasing each variable. We are only increasing the ratio. The ratio is made up of each variable. If you look at this definition, because you have one input and one output, it implicitly assumes constant retention scale. But in a world of variability and multiplicity, constancy doesn't always work. How can we then measure efficiency? Well, this is how we can. We can measure efficiency in a unique way, and that unique way is called weighted sum of output over the weighted sum of input. So watch this. Now we don't have one Y, but we have Y1, we have Y2, we have Y3, okay, all the way up to say Yn. The outputs are many. The same way the inputs are also many. So the question is that, in this case, you can't just go and divide the output by the input. And there are many. So you can also go and add the Y's together and add the X together, because the Y's are different. They are not the same Y. They are different. When you add all of them together, you're assuming that they all have the same weight. That's why you're adding them together, but they don't have the same weight. The weight for labor is not the same as the weight for capital. They all contribute differently to the company. That is why efficiency under complex setting is defined to be the weighted sum of the outputs divided by the weighted sum of the inputs. You're going to see the writing very soon, but I want you to understand the principle. The weighted sum of the output by the weighted sum of the inputs. The weights are called multipliers. And later you will learn that the weights are also called intensity vectors. Intensity vectors. The weights are multipliers, they are intensity vectors, They are the importance you attach to each input and each output before the efficiency of the unit is assessed. Keep that in mind. It's a weighted output. That's the general definition of efficiency. The weighted outputs over the weighted input. This is how you write it. So I take an output, say Y1, and then I attach the weight to Y1. Or I attach a multiplier called U1 to the Y1. In other words, for this particular output 1, it has a weight, an importance called importance 1 or weight 1, called U1 here. I have to weight the outputs one by one before I sum them. So this becomes the weighted sum of the outputs. These are the specifics, and then this is a summation. The weighted sum of the outputs divided by the weighted sum of them. The UI, the UR, and then the VI are the weights, the importance that you attach to the inputs. So if the U's are many, then each one of them will have a different weight. And that is what you apply to every firm. It's not one firm. Every firm will be, having that particular weight attached to it. Now, this weight is similar to what you know in linear programming as the dual. You guys remember that in any primal linear programming, there is a dual linear one. Do you remember?
Yes.
Good. That leads to, and we have that theory of complementary slackness theorem. So the dual that you are seeing above here, it has led to a new or some kind of new DEA models called dual multiplier problem. The dual multiplier models. And these multiplier models are usually compared with the envelopment model. If there's time, I'll show you the difference in the subsequent weeks to come. So the dual is the multiplier model, whereas you will learn later that the envelopment is a primal model. Take note of that before we get there. The envelopment is a primal model, and the dual is a multiplier model. Now, the dual model has got some characteristics, some attributes that helps to assess the efficiency of the firm in terms of ratios. Ratio, as you can see here, okay, ratios of aggregated weighted output divided by that of the aggregated weighted input. Okay, given the fact that similar ratios are calculated for all of the observed firms. This definition of efficiency is very important because you are going to see that it helps you to get a first-hand understanding of the linear program. See, any linear programming, which is a fractional program model, can be linearized. Any fractional programming problem can be made a linear programming problem. And that is why this definition we are having here is very, very important. Let's try to explain what the DEA model is. As you can see, it says that from here, the weighted output, say this is the output R, no, the weighted output, the word weighted is a W, the weighted output divided by the weighted input, they are sum. What does that mean? So what it means is that each DMU is allowed to choose the weight to maximize its own efficiency. But in the process of doing that, the same weight is given to every other firm to be sure that what this guy is doing to himself is the best way for everybody. Why should you? Because it's the best way for everybody, because we are all in the same production possibility set. And this whole choosing of weight by each firm, and then the same weight is applied to every other firm. Then when it is done, you go to the next person, he chooses weight, then the same weight is applied to every other firm. And when we finish, you go to the next firm, which chooses weight. Anyway, that whole thing has led to a new crop of work called weight restrictions and trade-off. And when this happens, when the units are allowed to choose their own weight, what it means is that we have given every firm, every unit, every DMU, every chance for him to look good, every chance for him to look good, every chance for him to be efficient. So it's not like one of them is going to say that, oh, I'm sorry, I'm inefficient because you chose a weight. That doesn't work with me. Managers love this approach, okay? Managers of the firms, they cannot go back and say that the results of the DEA is wrong, because they were all given the choice to choose weight that will help each one of them to be efficient. It's a beautiful thing. The weights are found. So in the programming, you will calculate the weight as part of the solution to the programming. And it is from these weights that you are able to fit in to get efficiency score. We shall look more on this in the process. Next time we meet, we are going to look at assumptions of DEA before we look at the practical aspect of it. What are the things that make DEA applicable? And you will notice that even though these are assumptions, they are not restrictive assumptions, they are practical assumptions. They are very practical assumptions. We'll learn the assumptions, then let's meet on during the week.